So in exercise 1103, we're going to look at some more trig identities. Now, these three here are given on your reference sheet, and I am going to be proving them. So sine of A plus B is sine A cos B plus sine B cos A. So it goes sine cos, and the AB swap places. So in the first one, I tend to put them in the same order. Because it's a plus, it actually doesn't matter. For cos of A plus B, it goes cos, sine, and the sign switches. For sine, it stays the same. And that's the same as derivatives too, of course, so that's a good way to help remember that. For tan of A plus B, you add them on the top, tan A plus tan B, over 1 minus tan A tan B. This sign will be the same as that one, and this one's the opposite of that one. So what we can actually do is extend these rules out to if they are negatives. So on the reference sheet, it doesn't give it to you as negatives, but you can do it. So if this was a minus in here, this will become a minus here. So these two, they're always the same. With cosine, they're the opposite. So if that's a minus there, this one becomes a plus. And with tan, if that's a minus there, this one will become a minus, this one will become a plus. So this one is the same, and this one is the opposite. Okay, so in order to prove this, I'm going to start by proving cos of A minus B, and then we're going to work out the other ones from that one. So if you look down here, I've drawn a unit circle. This angle here is B, and the whole angle from 0 around to this one is A. So the angle in the middle is the difference between those. So this angle here is A minus B. So I'm going to join those lines up to make a triangle. So of course, as we've seen before, the coordinates of this point, the x coordinate here, if I was to make it a triangle, is cos of this angle, because that's x over 1. And the y coordinate, y over 1, is sine of angle B. So same thing up here, cos of angle A is an obtuse angle here all the way around. And so cos A for the x coordinate, sine A for the y coordinate. And of course that x coordinate would be a negative number, because it's negative that way, which tells us, of course, that cos is negative in the second quadrant. Sine stays positive because it's the y coordinate, so it's going up. Okay, now what we're going to do is have a little look at the distance between here and here. Now I'm going to find actually the distance squared, so PQ squared. So this is point P, this is point Q. The distance between them using the distance formula, we know that PQ squared equals y2 minus y1 squared plus x2 minus x1 squared. So and remember, because there's a plus, you could do the x's first or the y's first, it doesn't matter. So that's the distance formula, but squared on each side, because normally we say PQ equals the square root of all of that. So let's work out what that is. So let's make that point Q as our y2, x2, y2, and we'll make point P our x1, y1. So y2 minus y1 squared would be the same as sine A minus sine B squared plus x2 minus x1, which is cos A minus cos B squared. Now I'm going to fully expand that out and simplify it. Now just for space, I'm going to actually start right over here because it's going to end up a bit long. So perfect square, so sine squared A minus 2 sine A sine B plus sine squared B plus cos squared A minus 2 cos A cos B plus cos squared B. Now let's have a little look at what we've got here. We know that sine squared A plus cos squared A equals 1. We also know that sine squared B plus cos squared b also equals 1. So together that's 2 plus, oh, in this case minus, so minus 2 sine A sine B minus 2 cos A cos B. Now I'm going to stop there for a minute with that one, and I'm actually going to find that distance again using the cosine rule. So I've just written down the cosine rule here. So our C is going to be this line here. So our capital C is that angle A minus B, and our A and B are those ones there. So what we end up getting here is that our PQ squared is equal to OP, because this point here is the origin. So OP is that one squared plus OQ squared minus 2 times OP times OQ times cos of the angle between them. Now, the cool thing is that OP and OQ, it's a unit circle, so they both equal 1. So OP equals 1, OQ equals 1. So let's write that out again. So PQ squared equals 1 plus 1 minus 2 times 1 times 1 cos A minus B. So that's equal to 2 minus 2 cos A minus B. Now, if you compare this one and this one, they're both formulas for what PQ squared is equal to. So we can make them equal to each other. So 2 minus 2 cos A minus B equals 2 minus 2 sine A sine B minus 2 cos A cos B. Now I suggest you actually pause the video just here and try and simplify that yourself. Okay, so I'm going to minus 2 off each side. I'm just going to do that by crossing them out. And I'm going to divide each side by negative 2. So divide negative 2, divide the whole thing by negative 2. So what I get is that cos of A minus B is equal to sine A sine B plus now cos A cos B. Because it's plus, I can actually turn that round just like they have on the reference sheet. So put the cos's first, so cos A cos B plus sine A sine B. Now we're going to use that rule to prove the other formulas as well. So in order to prove the one about cos A plus B, I need to use these rules. So we saw these angles are in quadrant 4 if we're going clockwise instead of anti-clockwise. Because they're in quadrant 4, cos is positive, sine is negative. And also because of being odd and even functions, which I'm actually going to mention in the next exercise as well. So what we're going to do here in order to prove cos of A plus B is we're going to replace all of the b's with negative b's. So replace b with negative b everywhere. So that's going to be cos of A minus negative b equals cos A cos of negative b plus sine A sine of negative b. And now we're going to use these rules to simplify that. So this just becomes cos of A plus b. Now cos of negative b is just equal to cos b, okay, because it's an even function. So cos A cos b. So the negative just disappears for an even function. Sine of negative b is a negative. So that's going to become minus sine A sine b. So when you've got sine of a negative, the negative can come out the front. And there's that second formula proven. I just mentioned too, the reason we do cos first and then sine is because it works so nicely with this one and just to keep some consistency with those. Now I'm going to start now proving the one for sine, the sine, angle, sum and difference formulas. And in order to do that, I'm going back to this formula again, and I'm going to replace A with 90 minus A. So I'm using those complementary angle results that we talked about in the last exercise. So the left-hand side, instead of A, I'm doing 90 minus A. There's still a minus B there. Equals cos of 90 minus A, cos B. Some people find this more comfortable if they actually change the variables. So instead of A, you put 90 minus X, and instead of B, put Y. And you can come up with a formula that way. But there's no reason you can't just switch a variable for another variable, as long as you do it consistently across the whole lot. So 90 minus A there, sine B there. Now we use our complementary angle results. So this left-hand side, that's the same as 90 minus A plus B, if I factorize out that minus. This cos of 90 minus A, well, we saw it's the complement of sine, so that's the same as sine A. We've got our cos B still. Plus sine of 90 minus A is the same as cos A, as we saw, because they're complementary angles. Sine B is still there. Now over here, 90 minus, we can use our complementary rule there as well. So that's sine of A plus B, because of our complementary rule, equals sine A cos B plus cos A sine B. And that's that first formula that is on the reference sheet. That's the sine angle sum formula. Now in order to do the sine angle difference formula, I want to replace all my B's, replace B with negative B in that formula. Have a go at it yourself, pause the video, have a go at that, see if you can get the sine angle difference formula out. Okay, so we get sine of A minus B, because B has become negative B, equals sine A cos negative B plus cos A sine negative B. So sine of A minus B equals, now I'm going to use these rules again. So cos of negative B is just equal to cos B, because we're in the fourth quadrant where cos is positive, or because it's an even function. Now, sine of negative B becomes negative because it's an odd function. So that minus is going to come up the front. So minus. Now, I'm just going to write the sign first, because that's how I had it written on the previous page. So 2 times 3 equals 3 times 2. It doesn't matter which order I put those in. And there's the sine angle difference formula. So I've proven now those first sine and cosine ones. It's now time to prove the tan formula. And for that, we're going to use the fact that tan is equal to sine over cos. So let's have a go at that. So let's start with tan of A plus B is equal to sine of A plus B over cos of A plus B. So sine of A plus B is sine A cos B plus sine B cos A. And in our denominator, cos A plus B is cos minus sine. Now to work this out, what I'm going to do is I'm going to divide the numerator and the denominator by this thing here, by cos A cos B, top and bottom. So I'm getting a bit squishy for space here, but I really want to show all my working. So this first one becomes sine A cos B over cos A cos B. Now I'm just going to pause my video and fill it in. Okay, so I've just written cos A cos B under each of those 4 terms. Now let's have a look and see if we can simplify some of these. So you can see here there's a cos B there and a cos B there. They are going to cancel out. Over on this one, we've got a cos A and a cos A. They cancel out. Here, cos A cancels cos A, cos B cancels cos B. This whole thing will just be 1. And here, we've got nothing that cancels yet. Now, let's have a look at what's left. So, this first term is now sine A over cos A. Well, that is just tan A. Plus, this second one is now sine B over cos B. And that is just tan of B. Down here we've got 1 minus, now sine A on cos A is tan A, sine B on cos B is tan B. And that's the formula, the tan angle sum formula. Now, have a guess how we're going to prove the tan angle difference formula. Just like we did before, we're going to replace that B with a minus B. So let's have a go at doing this. Now for this, we are going to need this rule here. Of course, tan is an odd function, so it's negative. Also, we can think of this as being in the 4th quadrant where tan is negative. And I'm going to use that here. I'm going to replace all my B's with minus B's. So I'm going to get tan of A minus B equals tan A plus tan of negative B over 1 minus tan A tan negative B. So tan of A minus B equals, so that's just tan A. Tan of negative B using this rule becomes minus tan B over 1 minus, well, we've got negative here, so that's going to become plus tan A tan B, and that's the proof for that one. So I've now proven all 6 angle sum and difference rules. Angle sum for sine, cos and tan, and angle difference for sine, cos and tan. So all 6 of those rules are proven. Now I will just mention too, if you had, for example, cot of A minus B, that's tan flipped upside down, so you could just flip that upside down as well. So you'd actually get this rule, and I've recently actually been using this with my year 12 class. So, and the same would go for cosec and sec is flipping upside down, but that tan one's going to come up a bit more often. So let's look at some examples. So the first one is find the exact values of tan 75. Now, anytime it says exact values, you're looking at your exact value ratios. Now, what we want to do with these generally is look at some combination of 60, 30, and 45. So the idea is to split 75 up with those. Now, if I did 60, it'd be 60 plus 15, there's no 15 there. If I do 30 plus 45, that's great, that works perfectly. So that's the same as tan of 30 plus 45. So there'll be some sum or difference of these numbers most of the time. So we're going to use our formula here, okay? So that will be equal to, so we've got a plus, a plus minus, add them at the top. So tan 30 plus tan 45 over 1 minus the product of those two. So 1 minus tan 30 tan 45. So let's have a look at this. Okay, so from this triangle, tan 30 is 1 on root 3. So 1 on root 3 plus tan 45 is 1 over 1 minus tan 30 is that 1 on root 3 again, times tan 45, which is 1. Now, when you get fractions within fractions, the first thing you should always do with that is just multiply the top and the bottom by that root 3, just to make that a little bit nicer. So 1 on root 3 times root 3 is just 1. 1 times root 3 is root 3. Over root 3 times 1 is root 3 minus root 3 times 1 over root 3, which is 1. Now, they may also want you to rationalize your denominator. So remember, we would multiply by root 3 plus 1. top and bottom. Now you can see there those numerators are actually the same. So one way to write that would be 1 plus root 3 all squared, which I might do here, 1 plus root 3 squared over, now this is now a difference of 2 squares, so that squared minus that squared, so that's going to be 3 minus 1, so over 2. Now we could just leave it as 1 plus root 3 squared over 2, or we could expand that out, which is what we're normally expected to do. So that's 1 plus 2 times 1 times root 3 plus root 3 squared all over 2. So 1 plus 3 is 4, so 4 plus 2 root 3 over 2. And we can simplify that down quite easily because everything's even there. Let's divide the top and the bottom by 2. And it becomes 2 plus the square root of 3, and that's the exact solution for tan 75. Now in example 2 we want the exact value of cos 120. Now there's a few ways you could do this one. The easiest way to do it would absolutely just be saying 120 is there, find the angle to the x-axis, this is 180, 180 minus 120 is 60. Second quadrant, it does equal the negative of cos 60, and cos 60 is half, negative half. You could even check that in your calculator. But I'm also going to show you we get that same result using this formula. So you could say that cos 120, you've got two choices. You could do cos 180 minus 60, or you could do cos of 90 plus 30. And either one will work. Remember, if this is minus, they switch. I might do this one actually. I was going to do that one, but I've changed my mind. So using the cos angle difference formula with the minus, we go cos 180 cos 60 plus sine 180 sine 60. Now cos 180 and sine 180, you can literally just do them in your calculator, or you can think up here over here and think about the x and y coordinates. So if you're right over here at 180 degrees, then the coordinates of that point are negative 1, 0. So therefore cos 180 equals negative 1, sine of 180 is equal to 0. So remember, cos is your x and sine is your y because of that adjacent and opposite. So cos 180 is negative 1 times cos 60. Sine 180 is 0. So I'm just going to leave that as all as 0. Oh, let's write times sine 60, but obviously that'll disappear. And you can see that's exactly the same as what I wrote up here. And that is negative half. So it is an option. That's by far the easiest way, but I'm just showing you that it still works here as well. So in example 3, we're asked to simplify this, and that's just a matter of recognizing this as the cos angle difference formula, because remember, cos the sign switches. So that is literally cos of 3x minus x, which is simply cos of 2x. Now that leads into actually the next part of this, where we look at what's called a double angle formula. If you wanted to, you can actually expand this out a little bit more too, and we'll look at that in a moment.